Basic data structures. When we finished off last time, we hinted at how we could build more complex data structures from the base types we covered. That's exactly what we're going to do today. So let's get straight into it. Lists. In everyday speech, a list means a sequence of something, anything, all written down in the same place for convenience. That's pretty much exactly what list means in programming too. In Python, a list is declared using square brackets, like this. Inside those brackets, we write the elements or items that we want, separated by commas. Those items can be pretty much whatever we want them to be. They can be strings, floats, integers, booleans. We can even mix and match different data types in the same list. We can define elements as literal values using expressions or even as variables. Important to know is that lists are ordered. They're not just a jumbled set of elements. Each item comes after one item and before another one, with the obvious exception of the start and end of the list. We access individual elements of a list like this. That is the name of the list followed by square brackets containing the number of the element we want. We call this number the index. Note that in Python, the index starts at 0. So what we might think of as the first element is stored at the 0th index, the second element at the first index, and so on. We can also use this syntax to redefine elements in a list. What we can't do is reference an item number that doesn't exist, or an index out of bounds, as Python will call it in the error message you'll get if you try. We can add items to the end of a list using .append, or insert them at a specific point using .insert, which will shift everything afterwards up an index. We can also remove elements of a certain value using .remove, or at a certain index using .pop. These are examples of list methods. There are actually more than this, but these are 4 of the most important. You'll easily be able to find all of them by looking at online documentation. Lists are our first example of a collection data type, i.e. one used to store multiple items of data. And we're about to meet a few more. Dictionaries. Next up is dictionaries, another collection data type. Again, think what the word dictionary means in common English. With a dictionary, you look up a word and you find that word's meaning. In computer science, we call this mapping. The idea that one value points to is mapped to another. We call this first value the key and the other value the value. A bit like a chart or a map legend or, well, a dictionary. Python's inbuilt dictionaries implement this mapping. That is, they allow you to store and retrieve key-value pairs. In Python, we can declare an empty dictionary like this. Let's see how this works with a simple example, by mapping people by their name to their favorite color. Dictionary items use a very similar syntax to lists. That is, the name of the dictionary followed by square brackets. Only instead of an index number, like lists, it is in these square brackets that we write our key. We then define it, that is, assign a value to the key, as whatever we want. We access it in the same way. Let's add a few more. This raises an important point. We are allowed duplicate values. That is, 2 separate keys pointing to the same value. See how Dio and Bob both have the same favorite color, red. What we cannot do is have 2 values assigned to the same key. That is, one key pointing to 2 things at once. If we try this in Python, you'll see that we only end up replacing the original value. Maybe now you have a question. Surely that's not like a dictionary at all. With a dictionary, a word can have more than one meaning, say rock, which can be either a big lump of mineral or a type of music. Unfortunately, in Python, we can't do this, but we can fake it. A key can only have one value, but that value can be a collection with multiple items inside it. If Charlie has two favorite colors, we can assign their value as a list. And yes, if you are curious, you can have a value in a dictionary be another dictionary. In fact, you can pretty much nest any data collections you want. You can have lists of lists, dictionaries of lists, lists and lists of dictionaries of lists, etc. Just keep in mind that it can get messy very quickly. Dictionaries, like lists, and like all data types in fact, have several built-in methods to help make working with them easier. We won't be going over them all, and you'd be unlikely to ever use them all in a single program, but we recommend taking a look at them. They're easy to find, documentation for, online. A brief pause. Dictionaries and lists are by far the most commonly used data collections in Python, and thus the two most important to understand, hence why we went over them in as much detail as we did. But there are still two more built in to Python, with their own special syntax. While not used as much, they are still important, and both have cases where they are the best or even the only real choice. Thankfully, once we do understand lists and dictionaries, the remaining two can be explained pretty simply. We're going to go over them briefly. Sets. Sets are actually very simple. They're like lists, but they're completely unordered. Sets are like a jumble bag of items. They also can't have duplicate items. An item is included once, or not at all. In Python, sets are written with curly brackets. You might be thinking, if they're unordered, how do we access specific elements of a set? And, well, you don't. You can add items, remove items, get all or some of the items at random, but you can't say pick the first one because there is no first one. They're all mixed in together. Tuples. Tuples, also very similar to lists, are written with round brackets and comma-separated items, and accessed with index numbers in square brackets. The big difference with tuples is that once they're defined, you can't add or remove any elements from them. They're like lists that get locked shut as soon as you define them. You can't replace any items either. If you try, you'll get an error. You can change the elements without completely overriding them, if that's possible, which depends on the data type of the element. For example, you can do this, but not this. Summary. Data structures like these allow our program to be a lot more flexible. They also introduce organization, which is essential for many different algorithms. It's also just nice to have for us. It can be a lot easier to visualize one variable with a list of 10 different things all in a set order than just 10 different variables with different names and no way to order them. Although, of course, which is actually better always depends on the problem you're trying to solve. Not only is learning these data structures important for learning programming, but observing how they build off of the fundamental data types and how, in turn, we could see more complex functionality emerging by using them is exactly the kind of logic that will serve us very well, not just in learning to code, but in coding itself.